Like, deeper in the house.
Shut up.
Where's the dinner at? Just like, you can't do that.
Can Norfolk hear us? Well, okay.
I was 12. Oh my God, it took me 500.
You're a nice one.
Yes. I don't care what they think about me. I'm almost like, just like old girl who was eating the salad. Oh, you seen that fork going? So,
What do you think? Sorry.
one day she was going to have in the corner eating salad. It's like, God.
It's really weird.
You eat vegetables.
Yeah, is there stir fry?
I guess it was better.
Okay, let's start, guys. Everyone. So I'll be talking about nanophotonics, another nano application. And good thing is that this is my own research area here. So I've been teaching you how to build things in nanoscale, the general foundations of nanotechnology. But now I'll show you what I've been working on myself here. Okay, so we need to start. Of course, I'm going to skip the first couple of things because I gave you this. This talk is generally a recruitment talk that I carry out in different universities. I generally start by saying, okay, so what is nanofabrication and how we do that? So they need to see the whole clean room, of course, how we create these devices at the nanoscale. We need the airflow. You guys know all about it now. This is our clean room here at NanoFab, the Penn State clean room. Okay, but the real discussion starts here. So since I'm going to be talking about nanophotonics, I probably need to tell you what photonics was. What is photonics in the first place, or what was photonics in the earlier days? In order to understand that, we need to start with the definition of light, and I emphasize that a lot during the first week, but light is a wave package, and just like the ocean waves, a much simpler wave actually. The physics is very different, but there's one thing still the same, and that's the definition of the wavelength, the peak-to-peak separation, as you guys remember. And the white light that you see on the left here is a combination of all these other lights, the colors on the right-hand side here. So we have like red color down to the UV light, as you know. And in this case, Newton's experiment is carried out, and Newton has shown that the light actually gets dispersed and gets into these different colors. Okay. So now, more about the wavelengths and the scales. You guys know that in the whole wave phenomena, right? This is the whole electromagnetic wave phenomena and the spectrum. Electromagnetic waves, when you consider them, optical spectrum is only here. Is only here, the little spot here, just this occupying this region. Whereas we have the radio waves, we have the microwaves. You fry your pizza with the microwaves, right? Norfolk? Anyone uses microwave there? No? Nobody uses microwaves? Yeah, you guys use microwaves, right? All right, so those microwaves are actually the wavelengths that we're talking about are in the range of millimeter range, but they still have a wave phenomena. They still have these ups and downs, the sinusoidal wave phenomena. It gets shorter and shorter, and we go down to the gamma rays. That's just a definition, and it's just related to the frequency. Of course, you know by now the frequency and the wavelength are inversely proportional to each other, and we can, once we know the wavelength, we can go to the frequency as an example. Right, we know that the radio waves are really large, but they're still showing us the wave phenomena. and I don't know if anyone there at Norfolk is also listening to radio anymore, but they're really large waves, at least when they were getting transmitted in the last century. We were using these antennas, right? And they're really large waves. The peak-to-peak separation was large. And then we have the microwave to fry our pizza. We have the infrared spectrum when we go down to the visible spectrum. So that photonics was mainly involved into the infrared and also the visible spectrum. So everything starts with this person. You guys remember this person, who this person is?
I remember the photo.
You remember the photo?
Oh,
Interesting. That's more interesting. So I've never seen anyone actually remembering the photo. Many people remember the name. What's the names, Emil? Snell's law, right? That's the Snell's law. That's Mr. Snellius from probably, I would say, 16th or 17th century. We have to check that up. I'm not sure. Anyways, what he was working on was the phenomena of refraction. So, anyone watched the movie Matrix? There was one important phrase, right? That there is no spoon. In this case, there is a spoon, of course. Everyone knows that there is a spoon. There's not like anything funny going on there. Anyone instinctively knows that, but there's the phenomena of refraction that is governed by this very simple equation, right? N1 sine theta 1 and equal N2 sine theta 2. That means that everything, the trajectory of the light here, the rays, that's how we define it, is governed by the refractive index. And so if we have two different medium, like water and air here, the rays would be refracted, and that's how we see the spoon being refracted. It's actually a continuous spoon. So there is a spoon there. No. Anyway, so in photonics in the old days, we knew how these kind of slabs, these different refractive indexes, see what's going on here. The light is coming from the top, the sun is there, the light is just emerging, coming from the top, okay? And it has different wavelengths, two different wavelengths. This is the first wavelength, lambda 1. This is the second wavelength here. And we got a slab, a homogeneous slab, okay, made out of a different refractive index, inserted into the air. Why do I know that? Because n equals 1 here. That's like the refractive index of air. N equals 1 here too. And in between, I have a refractive index of 4. What's happening at these two different wavelengths? Can you guys decipher what's happening already? We have a refraction phenomena going on. Reflection phenomena. So at the exit side here, all right, while the light is coming in, it kind of gets bounced back. So it gets interference here. So that's why I'm seeing a lot of light accumulation here. Whereas it smooths the propagate here, right? So all these things were very well known in the previous century, and they were making use of these kind of just relying on the refractive index change so far. So n is different in some medium, n is different in another medium. That's all they were relying on. So photonics was the method to engineer and guide the trajectory of lights, okay? So that we would process the light and we would carry the information with light, and all was relying on this refractive index change. That was it. All was relying on this gentleman, Mr. Snellius. Okay, so another picture here. We are trying to send our signal from point A to point B here, right? So if I have a slab again with a different refractive index, like n equals 1 all around in this area, and n equals 4 inside, okay, just an example, n could be different number too, what will happen? The light, as you know, will be trapped here because it will go through these little total internal reflection. You guys remember total internal reflection? It will not leak out. Total internal reflection would happen if my, let's say, if the light is coming from n equals 4 medium, okay, with some angle, and if it's trying to go to n equals 1 medium, the different refractive index, this n equals 1 medium would not have any defined sine angle, right? It would not be able to refract this. Instead, all of the light would be bouncing back. You guys remember that phenomena that we call the total internal reflection. Again, all due to the fact that these refractive indices are different, and I could really send my information from point A. Let's say I'm now sending in my information from Penn State here to Norfolk State, right? I could do that, and I was able to engineer these fiber optic cables, and you can see hopefully the total internal reflection much better here with a light source, with an LED. So light is getting bounced back and forth, and then it's trapped. It's propagating along the fiber optic cable. All right. So, and everything was relying on this refractive index distribution. So I have a different refractive index here. That would become my wave guide. It's guiding the wave, so as the name implies, it's just a wave guide. And once I get my information from one point, the other point received information. That's what I aim. Okay, so and then I would end up with these kind of nice configurations where, let's say I'm trying to send my information from, again, let's say Penn State to Norfolk, but in between, someone might be trying to steal my information, or might I don't want to direct it there, so let's get another channel. I don't know. Someone is listening here, okay? So I'm trying to engineer some, like these kind of ring resonator, that's what we call it, and we could guide the light so that the light would pop from this side and would be going to the exact place that I'm aiming for. This was very useful because we could engineer the pathway for the lights. All right, so the light would go to a certain direction that we were aiming for. Any questions so far? That's all about still photonics. That's everything done with photonics, everything done with Snell's law, everything done with the difference in the refractive index. We could engineer that. And then what did we do? Well, we transformed everything to optics and optics information propagation. We built these fiber optics cables in between even continents. You guys know that, let's say you're a Bayern München fan, okay? Anyone there in Norfolk that's a soccer fan, Bayern München, European football maybe? Oh, you are, wonderful. Yeah, myself too. So maybe you would like to check your favorite team's website, Barcelona, or I don't know, Real Madrid. So what you would do is you would rely on the information that is like propagating through these kind of channels, these fiber optic channels. Everything was handled like those Ethernet connections are handled by these fiber optic cables that are installed at the bottom of the ocean. Okay, so that's good. I now hopefully convinced you how we transmit the light from one location to the other. That's good. But then you would ask, then I would need a receiver on this end and a transmitter on this part. Well, then I would have to build photodetectors. They would be my receivers, okay? So if you remember our discussions, just giving you a clue, but these photodetectors would be your diodes, okay? They are the similar diodes that we looked into, and then we would have light emitting diodes too. That would be my transmitter. So I would have my nice light source, and I would have my nice collection means to absorb that light and process that information too. I would have to change that information into electricity, right? I can't just immediately process the light information. You guys agree? So I need to have that processed into something meaningful in terms of voltage. Okay, then these two gentlemen came and they said something new. And I'm quite proud because they're from my part of the geography. This gentleman, he is from Serbia originally. Of course, he's a United States citizen. And this gentleman here is from Greece originally. So they said, let's make peace in Balkans. No, that's not what they said. They said, I wish they said that, of course, but they said something also very intriguing. Well, we're all the time relying on Snell's law and the refractive index distribution of these slabs. What if, one of them said, I'm going to give a driller to one of my postdocs, and I'm going to ask him over the weekend, well, I can do that. He doesn't have a life, right? All he has is his lab and his instruments. So that postdoc went into the lab and drilled some holes, and this is the outcome. So now what's different? Instead of a continuous slab, right, like n equals 1, n equals 2, we have now drilled holes. And you guys have learned how to drill holes. How do we do that? Lithography, right? That's what you do at the nanoscale or micron scale. So their idea was something very similar to what we discussed earlier. They said, well, we have these atoms in a lattice structure, like the diamond structure that we were examining earlier. And what we ended up was the band gaps, right? The band gaps for the electrons, because these atoms would be located in these lattice corners. And once you have that kind of a full periodicity, that would open up this band gap for which electrons would not reside. Then those electrons with these kind of energies would not be able to exist, propagate inside this kind of a atomic structure. They said, can we duplicate this photonically? Can we put these artificial atoms right now, okay, artificial atoms. We are now starting to engineer these artificial atoms. They don't exist naturally, but if we do it periodically, maybe we can open up a photonic band gap, and I will show you what I mean by that. So let's look at this example. I have again the refractive index change between these circles and the outside medium, as you can see. And I can introduce my light from here or from here, both ways. That's all fine. So it's a very similar structure to our, do you remember the silicon? We bonded the silicon, we showed silicon like that, right, on the 2D plane. It's very similar to that. Now, we're not sending electrons. Electrons was there to conduct the current, right? It's not electrons anymore. It's the light now. And we are investigating the propagation of light. And this is what's happened. So for the usual, that's the boring case. So this is very boring. Many people over there may be also bored over the whole training, huh? Boring. So that was what was happening. But now, with the periodic function, with those drilled holes, now I have this scattering of the lights, right? And the light is not propagating in the same fashion as before. That's very intriguing. Now let's do one more thing. I will plug that into my fiber optic system. So there's a fiber optic cable here and another fiber optic cable here. This is the transmitting side, and this is the receiving side. And I have drilled my holes. How did I drill my holes? Like the nano patterning methods that we have employed. Like now you guys know nano imprinting, for example, or e-beam lithography, or normal optical lithography, right? And then some etching, reactive ion etching maybe, right? And then I would transmit the light accordingly. So this is exactly what happened when I tried to send my light from left to right. They have looked into the transmission spectrum. So let's look at this. They have seen that, and this part is the transmission. So I will say that this is T. How much of the light that I got? They have seen that for a certain frequency band, okay, so for the certain frequency of the light that I'm trying to transmit, just you can tilt your head a little bit to the left and you will see that I have no transmission. This is 0. I have full transmission almost in this band, full transmission on this band too, so those are band 1s and band 2s, but no transmission in between. And when I also tried to create the band diagrams, if you remember, that was my similar band diagram from semiconductors, I have something very similar. I have a band gap, and in this band gap, I have a forbidden zone. But now the forbidden zone is not for the electrons, not for the electrons. They are for the photons, for the light itself. So it's not the electricity conduction anymore that we're talking about. We talked about semiconductors, insulators, right? So you could tune the properties of the semiconductor. You could make it an insulator, more like. So in this case, we have like an insulating thing for the photons this time. And now let's take 2 points here. One is from this band here. Okay, so that corresponds to transmission. So I have transmission 100% here. And in another point that I just captured, I have transmission 0%, right? So, and then let's try to see how the response will be in the overall response of the light. Now, what I'm capturing is their frequency, actually. So I'm capturing two frequencies. One is from 240 or so. The other one is like 170 or so. These are the 2 points. So in short, I will send two frequency or two different light energies, okay, to the same drilled holes. I hope you can see it on your side too. So I have like a block, but now I have this refractive index change because I have like drilled holes here. So as a result, once the light is coming in, what is happening? At the point where I have no propagation, where I have an insulating material for the light here, there is no transmission here, it falls inside the band gap, and that's what we mean by the band gap, because the light is not transmitted for that frequency. So that's a no frequency, no transmission frequency. And as we switch to the band that allowed the transmission, that's this point, the other point up there. It's this point here. At that point, I have now already obtained my transmission, so I can transmit my light there. This is wonderful because I can make use of this configuration. How? Well, let's go back to the structure. They said, okay, so it doesn't conduct, it doesn't transmit in this portion. It's an opaque material in that portion. What if I just omit drilling holes somewhere? Like say I intentionally create a defect here in the middle, and it's not going to be drilled. This hole will not be drilled here, okay? So what's the response? The response has been, very interestingly, I obtain a very sharp, look at the axis. Now this is again transmission, and this is the frequency. Normally I had a band gap here, remember? But for the crystal structure with no defects meant that I would have band gap here. As soon as I introduce the defect, I have a very sharp band of transmission. You guys must remember this from our earlier discussions in semiconductors too. Now we introduce a defect into our semiconductors, so it's not like silicon nicely bonding everywhere, but I have, let's say, a phosphorus atom here. That's equivalent to that. And that phosphorus atom, as a foreign material, is now like kind of acting like a defect structure in the overall crystal. Okay. And what's going to be the outcome? So this is the structure. As I was saying, we intentionally omitted drilling this hole here now in the middle. No hole here. Very interestingly, the light pops into that drilled hole side, and this is the intensity of the light. We call it with I. The light gets increased there. The intensity just gets localized there, and it gets immensely increased. Okay, so let's go one more step. So if we intentionally not create these defects and not drill the holes along the way, like you can see here. Once the light comes in at that no transmission band, this was the no transmission band, remember? Now the light has nowhere to go. It will just follow whatever I'm doing. I can bend it like this. And this is very useful because if you ever work with a fiber optic cable, and if you ever try to bend it like 90 degrees and try to still transmit the light with the fiber optic cable, you would see that the fiber optic cable would give you a lot of leakage here at the corner. It would leak tremendously, and then you would lose a lot of light. It would just, the laser light would leak out. With this configuration, it cannot. Why? Because once the light is going through this side, it's going to say, oh, I can't reside in here because that's still the band gap for this light here, for this frequency of the light. And I can do more. I can say, oh, I'm going to open up this portion too, right? I'm going to continue creating intentional defects there in the crystal structure, so the light will be transmitted 50-50 in both directions. Great. What will happen if I send my light here still, but if I now do not create the crystal here? See, I did not create the crystal in this portion. Well, the light immediately starts leaking again because I don't see that nice band gap for this light here again, because the band gap is created whenever I have these nice crystal periodic formations. If I omit doing that, I go back to the leakage again. And the good thing is I can never do that easily with the fiber optic cable. So this is just a simulation that is showing you with the refractive index so change. So let's say that you have a slab here that has a T shape, okay? And this is all air. This is air. This is air. This is air. And I have a slab here, a T slab. So you see, I don't have that kind of nice guidance here. So that just said guys themselves to each other, wow, the Serbian guy and the Greek guy said, we open up a new research field here. And that's what they call the photonic crystals instead of the nice crystals that we have in for electronics, right? Where do we see these photonic crystals in nature? Well, we see them on like the wings of this butterfly, this blue morpho butterfly. Once you look at the wing under the scanning electron microscope, you see these nicely drilled holes. Evolution has driven this butterfly wing to obtain these kind of drilled holes. Okay, and then if you take a cross section and if you examine that electromagnetically with simulations, okay, that's a little more boring side, I would say, you would see that the blue color is getting reflected back because it is again a photonic crystal. Because once you get the intersection like it's shown here, you see that it's a periodic refractive index change. That's like a staircase, right? So I have air in this direction, in these dark regions, and I have material, organic material. They will have a different refractive index. So accordingly, once the light comes in, the blue light gets reflected, whereas the red light gets scattered, so it goes into the wing. And what color do I see this blue morpho? Well, I see the blue morpho having blue color because that's the color that is reflected back, right? So I see blue color here on the blue morpho, and I also see that the physics, the light interaction with these periodic arrangements should also reflect back the blue color and should just scatter, should get rid of the other colors. And this is called kind of what we call the biomimicry. People got inspired from these, let's say, blue morpho butterflies, and they said, can we create structures like these for our own engineering? And this is another example of biomimicry. There is this beetle here that you see on the left, and there's a specific thing about this beetle. Once the weather is humid, okay, it's wet, the beetle's original color gets changed and its back turns into a bluish color. So let me change my color here too. So it becomes bluish, as you can see, when you have wet humidity. When it's dry, it still gives you the same dull color here. So the researchers said, what's so important? What's so different about this, the back of this beetle? And they looked at it under a scanning electron microscope, and they have seen the same, very similar drilled holes, periodic, okay, somewhat periodic, I will say. In nature, that's the best that you can find. And one other thing about biomimicry, people think that nature does everything perfectly, okay? Of course, it cannot. So this is evolution, of course, but we can do even better with our nanofabrication methods. So people said, oh, I can create a humidity sensor out of this, right? That's a great idea, humidity sensor. So what they would do is they would just pile up these poor beetles in their pockets every day and bring them around in their pockets and just take them out and just look at the backs of these beetles and then just determine the humidity level. Of course, that's not what they would do. They would go to the lab and they would do self-assembly. So you guys see the self-assembled structure here with the nanosilica, and then they would do more etching and they would create the pattern, a much better periodic pattern. Of course, there's quite a bit of resemblance, but they would do a much better thing that nature can do, and this would be a publication all of a sudden, and that would create your humidity sensor. So in a very similar way, the photonic crystals here, they reflect back the blue color while they do not touch the other part of the spectrum, okay? The blue color gets reflected back when there's humidity. What is happening when there's humidity? These holes are, up to some extent, filled with water. Do you guys see that? So it would again change its refractive index. So its refractive index no longer is 1 inside those holes. And overall, response of the photonic crystal will change. When there's air inside the holes and when there is water inside the holes, humidity will change its optical response. Okay, then they said, then we can create a nice sensors out of this. So this is what they did. They drilled holes, in this case, that like you can see on the left-hand side, and they put that on this kind of a substrate, and they built the sensor, and they added chemicals from the top. They sent their laser from the left, and they looked at the optical transmittance. So as you're adding the chemical, of course, it will fill up these little holes that you're having here. Or it would still reside on the surface, and that will also alter the optical response. So if these holes are smaller than 1 micrometer, they would not be filled perfectly, okay, because of the surface tension. But the liquid would still reside on the top, and that would also alter the optical response. So this is what they ended up with. Depending on what kind of material they have inside the holes, like air would give you this kind of a detection. Air would give you like that kind of a sharp, nice single peak. When you have a refractive index change of 0.01, then that would get altered to the green case. And if you do a change, like drastic change, like n equals 1, a refractive index change of 1, it would be altered to this. So what am I reading here? I'm reading the transmitted light, and this part is the wavelength, okay? The x-axis is the wavelength. So all of a sudden, I used to get my light at lambda equals the wavelength equals 1.57 something, and then it jumped up to 2 micrometer in the infrared. So I can say, okay, I have shifted my response, and I can say that I have this much of a refractive index change. It's very easy to build a lookup table. What I mean by that is now with a 0.01 change, actually we can't really see that kind of a shift. As you can see, it's still the same wavelength almost. But once we talk about a 0.1 refractive index change, we go up to 1.613. So you open up a lookup table, and then you see how much of a change corresponds to what kind of a refractive index change, and you can retrieve back based on the refractive index change how much material that you put in there. Okay, and then you can also do these kind of fancy things like the 90-degree bending of the light that I was referring to, but you can also jump the light to the other side and do very similar things that the photonics people were doing. So you can filter out the light, you can send your information, filter something out, and then also process your light information as well. So all these things became very popular at the turn of the century, 2000, early 2000 or so. And this is what I did in my research when I was a PhD student. I hope you guys will also pursue at least a master's degree. But so what I did was I also created this lattice configuration, as you can see hopefully, and then I send my light from the bottom. This was what I'm trying to aim. I was trying to get a diode, but it wouldn't be a normal electric diode. Remember, the electrical diode would conduct in only one direction, like in this direction. We emphasized that a lot. Now, in this case, I would like to get a diode for photons, for the lights, so that the light would be reflected back if I don't send it in the right configuration, from the right position. If I flip it, and if I try to send it from this direction now, I would have some transmission. So I obtained a light diode. So this is extremely important because all of our communication systems are relying on light. So if we have a very similar thing like a diode that we have in the electrical components, we can apply that to light, and that would make life much easier for our light processing. Okay, so a lot more has been done. Now let's think about more detailed thing called topology, but I will make it very, very simple for you. What is topology? So in the most simple way, let's go back to the spoon. There's a spoon again here. The spoon you can create without, like, you can sculpture a spoon, okay, without really adding anything, okay? You just get a bulk of material, right? You don't need to add anything else. You can just shape the spoon with your fingers. But a spoon does not have the same topology with a coffee cup, because the topology will change, because you cannot create a coffee cup by just shaping the bulk material. You need to attach a little bit of a handle here, right? So that little handle will alter the topology, and we'll say, okay, oh, these are different topologies. Of course, you can go to an even more complicated topology, and you can end up with the cathode. So that would include another addition of this kind of an addition. I don't know, maybe something else too. But these are topologically different because I cannot create them. I will create them only by adding a couple of other things, okay? Something very similar, I can change the topology of these photonic crystals. So I can make them like my spoon, and I can make them like my coffee cup. Why am I doing that? Because I would like to, again, the main idea is to transmit the light, engineer the trajectory of the light. Here is my light source. And here are the magnetic fields that I'm applying to this crystal. You see, I'm applying a positive magnetic field and a negative magnetic field here. That breaks the topology. Normally, what do you expect when you put a light source here? You expect that it would go equally in both directions, right? That's what you would have. No doubt, you wouldn't have a preference, but if you apply this external field okay, in a very intelligent way, you can break the topology that exists in the nature, and you can force the light to go in only one way. All right? You can alter the magnetic field, and you can make this one negative right now, and this one positive, okay? The magnetic field will be applied differently. So, as you expect, the field will go in this direction right now. These are all simulation results, and that's what I do. I'm a numerical analyzer. I do theory, and I create these kind of simulations, predictions for the, especially the interaction of the light with nanostructures. Okay, then why could that be useful? Well, that could be extremely useful when you're thinking about your connection systems under the ocean. We said that United States and Europe is communicating with those fiber optic cables. Let us say that underneath the ocean a shark comes along, okay? And it will be a problem for our fiber optic cables, and it will say, oh, I'm gonna bite these things, or an obstacle, some obstacle, okay? So if you break the symmetry in the nature, if you make these two different topological systems all of a sudden by applying these magnetic fields, one is a coffee cup, the other one is a spoon. Even if there's a scatter, a material in between, I put my light source, I'm trying to transmit my light. What would happen normally is, if I didn't break the symmetry, if I didn't apply these magnetic fields, the scatterer would just scatter all the field. I would be lost, losing all this field, okay? It would just be lost. But thankfully, I have now made sure that the light would nicely, without any scattering, would still follow my projection in this direction. So, what does that mean? Even there's a shark in the ocean, no problemo for me. I can still guide the light nicely. All right, so how can I use these photonic crystals? Well, they're already in use. So you know your fiber optic cables, once you cleave them, they will look more like this. Like you have the fiber cable, you have like a jacket underneath and a cladding. All these are because you have a refractive index change. Just similar, the same 400-year technology. I hope you guys understand it now. It's the same Snell's law, and I have a high refractive index here and a lower refractive index as I go to the outer shells. So now they said, what if I drilled some holes inside that little fiber optic cable? Then I can confine and I can guide my light much more intelligently. So you see the halo core, for example. These fiber optic cables are suffering a lot from losses. So if I confine my light in that little area, because now everything is controlled by photonic band gaps, and I have the full control, full confinement control over the light, I will not have that much of a drastic loss problem anymore. So I can propagate my light much more efficiently. So these fiber optic cables are in the market. They are still a little bit more expensive than your normal fiber optic cables, but they are extremely useful because they don't belong to the same 400-year technology of coming from Snell's law. They are using a band gap creation just like your electrical devices, but for the light now. So the light cannot reside at any energy or any frequency, but you have the ultimate control to confine, to get rid of the losses for the light. So the ideal thing would be like this is your air hose inside your fiber optic cable. If you can guide the light in this little area, and that's what you're seeing here, the intensity of the light, that would be super fantastic because now the light is being transmitted inside the air, right? This is drastically different from what Mr. Snell is doing. We have the core, and that has the high refractive index. Optically, all these materials are lossy, so they will present a lot of losses. So if you replace this light confinement and light transmission from the core, the high refractive index material, the lossy material, to an air gap like this one, that would be the ideal case, because air does not have any losses, as you guys know, and that would give us a beautiful transmission with minimal losses. All right, now we covered the photonic crystals. I will touch the metamaterials in the remaining time, however time we might have. So metamaterials. So whenever you're presented a notion, always go and check what this adds up to, what really this means. Metamaterials. Meta, coming from Greek, means beyond. These are materials that do not exist in nature, okay? Very similarly, like the same Serbian and the Greek guy, they said, maybe we can create atoms and meta-atoms this time, and then we can build up our structure for optical design. So, what do these metamaterials have? Well, every material, as you might have heard, have these two important properties in terms of light. One is the dielectric constant epsilon, right? That's the dielectric constant epsilon. The other one is the magnetic permeability for the material mu, okay? So every material has a dielectric constant and a magnetic permeability, epsilon and mu. The thing that you might not have heard is that the multiplication of that gives you the refractive index, and the square root of that gives you the refractive index. So a lot of those materials that you guys know, like glass, relies here, where the refractive index is plus, because it's a positive number, because both the dielectric constant and the magnetic permeability are also positive numbers, okay? And their multiplication gives you a positive number too. Whereas the opaque materials, the absorbing opaque materials, have a different condition. They have the dielectric permittivity and the magnetic permeability. Getting one of them is going to get a negative number. So in the case of metals, for example, metals are opaque, right? They do not transmit the light. Why? Why do they just die out, kill the light that is going through? It's because their dielectric constant is a negative number, okay? And once you multiply a negative number with a positive number and take the square root, it will become an imaginary number. So your refractive index will become an imaginary number, all right? It's very similar for the case where you have magnetic permeability negative and dielectric permittivity positive too. So that will again become opaque. So people were all aware of these three quadrants. They knew that they had glass, they had metals, and they had magnetically active materials in the fourth quadrant. So these were all well known. The thing that wasn't known was, what if I have a material with both dielectric permittivity negative and magnetic permeability negative? So that means that I have both, like an opaque material kind of properties with negative permittivity and negative permeability. What will happen? So this is what happened. So you stack the atoms, okay? Look at this. This is what I do with my graduate students here. The equations are not important, okay? Don't be concerned about the equations. I'm trying to show you the general idea. We're stacking atoms. We are creating the atoms one by one, and this would be my one atom. That is made out of a material that I can find from nature. Nature provides me with a material that has a negative permeability. The nature also provides me a material that has negative dielectric permittivity. What if I just glue them together to create my, what we will call a meta-atom, okay? This is something that doesn't occur in nature. I'm forcefully, with my hands, I'm putting them together, and I'm stacking that and I'm building a crystal structure, a periodic configuration. What would you expect if I send the light from the left? So you know that negative permeability or negative permittivity, when you have them, the light should not go through, right? It should be opaque, right? So this is very strange. This is what they found. And this is what I expect my graduate students to calculate. Once you put them together, you have a very good transmission for a certain frequency band. All right, so that should be very striking. I put two things together that are supposedly not transmitting the light by themselves. So I put a little metallic sheet here, for example. I put a little metallic sheet, a very tiny metallic sheet, and put another one here, and I put something that is magnetically not transmitted too. But once I cascade them, they become opaque. They become transparent all of a sudden. That should be very striking for you. And that is what the metamaterial is. And ta-ta! This is what actually this guy told about it in 1967 or 8. His name is Dr. Vesalago, and I had the privilege to actually meet with him too in Germany. He's still giving seminars. He is the godfather of the field of metamaterials. He said in those days, I will open up the curtains there, and I will just by theoretically propose another kind of material that will have both the dielectric permittivity and the permeability negative. And he said this material would give me not an imaginary number for the refractive index, but a negative refractive index all of a sudden. And people were puzzled. A negative refractive index? Come on, we were playing with the Snell's law for 400 years. Now all of a sudden we're starting to think about negative refraction. The sad thing is, as you guys know, in 1967 and 8, there was the blockage. There was no real communication channels between the Western world and the USSR. So, as a Russian scientist, he published his paper in 1967, and nobody read his paper for a very long time because it was in Russian too. So we had to wait for a very good amount of time till 1990s till people figure out that, okay, so this guy came up with an idea and maybe we can apply that to our systems. And actually, thanks to him, I obtained my PhD thesis. So this is what happened. So yes, exactly like that. We are now building these meta atoms by cascading these two negative permittivity and negative permeability to obtain a negative refraction. So this is a slab, actually it's a prism, it's a wedge as you can see, that I built during my PhD, and I'm sending my light from the bottom. What is happening? Normally, let's look at the normal case. If I have a refractive index bigger than 0, right, that's the usual all the time, that's what I have. The incoming light at normal incidence would just propagate its passage with a normal incidence there. And once you come here, what do? You put a normal, right, like this, and then you would refract the light like that. But see, guys, the light is getting refracted like that. So this only means that the refractive index should be negative for this wedge. And it was a very tedious job to actually construct this wedge, because now you have to not just create the wedge, but you have to create every bit of the meta atoms that will create the wedge altogether. Do you guys see that? So you have to engineer every one of these atoms and put them together to make sure that the overall structure will show a negative refraction. All right, something not so boring finally after so many years, 400 years, in the case of optics. Now you can see the negative refraction much easier in these cases. Wedge structures, and then it's negatively refracted. So you can really alter the trajectory of the light. You can have like the light coming in and then getting negatively refracted, but you can engineer your meta atoms so that the outgoing beam can be like engineered to have like different trajectories in the end. This is awesome. This is like what you can do to actually send your information to Germany or send your information to Turkey, whatever you like. All right, then this gentleman came forward. Actually, he was the one who read Dr. Vasilagos' paper. I don't know how he read his paper because he doesn't know Russian as far as I know. And I also met with this guy too. He contributed to the field of nanophotonics to the extent that they knighted him in England. He is teaching in Imperial College, and his name is Sir John Pendry, thanks to his contributions to the field of photonics. So he said, okay, but this is not just the curiosity of the physicists, this negative refraction. He said, if you give me a negative refractive index, I can build you a super lens. So there you go. The little, you see his little picture there. So with negative refractive index, look at the negative refraction. So he's building a lens this time that will negatively refract the incoming lights. And there we go. We have a focusing happening here, but another focusing point at the exit too. And this would create, theoretically, super resolution. A much better resolution than that your optical microscopes can achieve. So you guys have heard about scanning electron microscopes and the resolution that they can get, right? So theoretically, this super lens can give you the same kind of resolution, but optically. So you don't need to have a scanning electron microscope. It's because the nature, the physics is just showing you with this picture. Let's say that you have something and information, the light that is coming from the left. This is originally decaying, so it's not supposed to go to the other side. But if you have your super lens, you're amplifying that signal and you're helping the signal to go out. This is how you actually get your super resolution. You amplify all those dying out signals, originally dying out signals. And then they got this. So they wrote this little pattern with what we call focused ion beam, just with ions on a surface, on a silicon surface. And they wanted to resolve that image. They used the super lens that Sir John Pendry used, and they get this nice image. Without the super lens, you can see how lousy the image can get. All right, so now you might be asking, like, how are these meta atoms? What do they look like? This is what they look like. Nothing really so fancy, I hope you can see. These are just periodic patterns that you can now create when you go to the lab, right? I hope you have now this kind of a confidence. These are like metallic depositions. Let's say I'm depositing gold, but periodically, like little metallic rods sitting on the horizontal plane, or a fishnet structure, like you can see here. That is, again, periodically created. The interaction of the light with these kind of patterns will give you the negative refractive index. The idea is to actually do an optical imaging even of the DNA that Terry was talking about. Because now you have a super resolution, and hopefully you will be able to get down to those kind of 0.34 nanometer resolution. Okay, another thing that we can come up with is, but the time is an issue. So let's see, we can have not a negative refractive index, but we can have a material that will have a refractive index that is 0. Why not? I can engineer my atoms so that they will have a negative, not a negative refractive index, but a refractive index of 0. And then if I send my light from inside this kind of a material, the outgoing beam will just preserve the shape of the structure that has this refractive index. You see the shape is looking like that. Look at the outgoing beam. It's almost the same shape of the original structure. Why? Because you can even know that, analyze that based on Snell's law. Let's say that my light source is sending this wave, this ray on the right. Let's put our normal to the surface. It's coming with this angle. What is going to happen? Well, normally it should refract, but my refractive index N1 is 0. So the only way for the light to go out is just to go normally at the outside. Because remember, N1 sine theta 1 is equal to N2 sine theta 2 for the outgoing beam. But N1 is 0. So that means that sine theta 2, regardless of what the outside structure is, N2 is, it should be 0 too. So I should have waves just leaving at normal incidence. Okay, so then I can create these kind of structures with zero refractive index. As you can see in the simulations here, however they go, they leave the structure at normal incidence. So this circular wave becomes all of a sudden perpendicular, as you can see. That's very important, and I won't be able to go into the discussion of the reasoning, but you can actually transmit the information. Let's say that this is your the fiber optic cable. Even if it gets larger like this, or even if you in the ocean you have like these kind of little narrowing portions, your light can still be 100% transmitted to the other side. Once you build your fiber optic cable with a refractive index almost equals 0, the fiber optic cable will not be attenuated, or will still transmit 100% of the light to the other side. Now let's go back to the more useful applications of the negative refraction. We said that we could build nice imaging with super lenses, right? We can adapt that super lens idea and the metamaterials to the MRI systems too, medical imaging. So you can employ those lenses for your patients inside these MRI machines to get nice imaging. Like in this case, you can create, now we're talking about millimeters range, but you can build your super lens in for those frequencies, okay? It's still the wave phenomena and can happen. And you can see that the patient's hand can be imaged right now with the Swiss roll, that's the super lens, whereas it wasn't imaged here without the super lens. So you can create these kind of structures to get the lensing, super lensing. And another thing is the cloaking device, the Klingon cloaking device. So this is what happened. These are the folks that are very, very famous in the field. So this is the guy who was working on the MRI machines here, okay, just as an example. And yes, this is Sir John Pendry. And this is my own supervisor here, okay. That's my own PhD supervisor back in the day. So Sir John Pendry said, well, if you give me those negative refractive index materials, I can create a cloaking device too. And that's what he did. He built a cloaking device. How did he do that? Well, that was the base of the Harry Potter too. There was a great hype about Harry Potter. And he said in his paper, as you can see in 2006, well, light goes a straight path. I agree with that. But what if I make a coordinate transformation? The light will still think that it was going straight a path, but now my coordinate has been intermingled. It's not straight anymore. It's not the same Cartesian coordinate system anymore. So if I put an object here, I can make sure that the light will not be interfering with that object. So this is what happened. They built these cloaking devices on the objects so that the light just went on as if it's not interfered with the wave. Whereas you can see that it leaves a lot of shadow at the back without the cloaking device. Well, you can see a much better image of the cloaking device and without the cloaking device. Now, I like to capture your imagination because I like to think about earthquakes. Earthquakes are also wave phenomena. And let's say this is your building. And let's say you'd like to cloak your building from the earthquake. And that's what people, researchers at Penn State are working on. They're trying to build not optical, but acoustic, large, very large, earthquake-wise large cloaking devices around the buildings so that the buildings would be cloaked and would not be interfering with the incoming earthquake wave. All right, then I will just wrap it up with this slide here. Sir John Pendry said, well, this cloaking thing is nice, but it's really difficult. He said, even as a young kid, I was cloaking my dirt very well under the carpet. So he said, instead of weaving like a 360 degrees cloaking devices, let's put everything under a carpet. He's a very nice fellow, that guy, Sir John Penry. So he built the carpet, the cloaking carpet, such that he would make the system virtually cloaked. So now you can see the structure that's now in the micron scale. You can see we have a bump here, and if your flat surface is interacting with the light, you're sending the light from the top, and you have a screen here, and you're trying to examine the light intensity. You guys can see that you just have one light beam emerging. If the light interacts with that bump, okay, then the light would be branched out, and it would have like these many ripples. Then you would see that the phenomenon of the uncloaked bump. But if you have this cloaking device that you create by carefully engineering the atoms up there, well, you're just doing some patterning, okay? That's it. Then you can put it on the top of the bump, and the light will not really see the bump anymore. The bump is being cloaked, so everything is now put under the carpet. Okay, so that's what we mean by putting under the carpet. This is my cloaking carpet right now. Right, it looks like it's 12 o'clock. Let's stop it here, and then we will eventually talk more about the plasmonics in the afternoon too. So see you guys in the afternoon. Any questions before we leave? Any questions here on this side?
I didn't really understand the copy screen.
Yeah, that's that really needs a lot of more detailed physical description, of course. Yeah. All right. There are no other questions. I will see you guys in the afternoon. See you, Pat. Yeah.